Hey everyone, we're going to continue on with our nervous system physiology about how nerve impulses are sent. So, in the last lesson, we talked about how the transmission of a nerve impulse is considered electrochemical. There's an electrical aspect as it travels down a neuron, and then there's a chemical aspect because we use neurotransmitters to go from one neuron to the next neuron. So, in the last lesson, we talked about the chemical aspect, how it travels down an axon where it reaches an axon terminal. Calcium channels open, calcium enters, causes neurotransmitters to bind to the surface. They cross your synaptic cleft, bind to receptors that allow sodium in, enough to generate a nerve impulse. In this lesson, we're going to talk about the electrical part of it. So, how do we generate that nerve impulse and how does it go down a neuron? So I brought up this picture last time, and the part that we're going to be talking about today is not at the synaptic cleft. The part that we're going to talk about today is how does the nerve impulse travel right here, down an axon. So how does it occur right here? So we're going to first talk about, well, what are the electrical conditions of a resting neuron's membrane? So in other words, what is this membrane like when it is not sending a nerve impulse? So what happens is whenever a plasma membrane is considered to be at rest, they are said to be polarized. What does this mean exactly? This means that there are fewer positive ions in the inside of the neuron's plasma membrane than the outside. In other words, the inside is more negative than the outside. If we're looking at ions, potassium is going to be one of the major ions inside the cell when it is polarized, and sodium is going to be the major ion that is outside the cell when it is polarized. And as long as the inside is more negative, means fewer positive ions than the outside, that cell remains inactive. What that means is no nerve impulse is sent. So here's an example of a resting membrane that is polarized. Again, notice we're taking a little snippet off of the axon. Potassium is inside, sodium is out. Notice the inside gets a negative sign because it is negatively charged, and the outside is positively charged compared to one another. So whenever an action potential is generated, it has to receive some kind of stimulus. So many different stimuli can excite neurons to become active and start to generate an impulse. We've talked about light excites eye receptors, or sound excites ear receptors, or you have pressure receptors or pain receptors. However, the most common is being excited by neurotransmitters that have been released by other neurons and have gone across that synaptic cleft to bind to receptors, which is why we talked about that last lesson. So whenever a neuron is stimulated, whether that be by light or by a neurotransmitter, it causes the permeability properties of the plasma membrane to change. So permeability is that it means allows certain things through. So for example, when it's resting, it doesn't allow ions to come in or out. However, if it gets stimulated, the permeability will change where it allows certain ions in. Specifically, the gates of the sodium channels are going to open, and so sodium tends to diffuse inside the cell. Whenever sodium rushes into the cell, it changes the polarity at that site. In other words, it changes the charge at the membrane on that site, and this is a process known as depolarization. So again, depolarization is when Na comes in. Here's a good example of it getting excited. It's going to show that sodium ions are going to come into the cell. and they carry that positive charge. This is going to cause something called a local depolarization, where right here in this spot where sodium is rushing in, the inside is going to become slightly positive. Now, if the stimulus is strong enough, or that means you have enough sodium coming in, a localized depolarization or graded response is initiated. And if there is enough, that localized depolarization will be upgraded and will eventually become an action potential or a nerve impulse that is able to be sent. All a graded potential or local depolarization means is that instead of the inside being more negative, the inside is actually more positive and the outside is less negative. So they've otherwise switched. So here is a good example of a localized depolarization. Notice that the outside is now more negative and the inside is now more positive. And then if you get enough buildup here, this signal is then going to be sent down the entire axon. Now, once you have a action potential nerve impulse generated, this is an all or nothing response, which means if the nerve impulse is generated, it's going to be sent. It's not going to be halfway sent or partially sent. It's going to go or not go. And one thing to note, now that we've known our anatomy, is fibers within that are covered with the myelin sheath tend to conduct these nerve impulses more quickly. So here is more propagation of your action potential. Our localized depolarization became strong enough, and notice how it's progressing across our axon or across down our neuron. Now, we can't keep our membrane where it has this charge indefinitely. So what happens right after it gets depolarized and the action potential is set is we have to repolarize it or put it back into neutral terms. So we have the permeability change again. It becomes impermeable to sodium ions. So that means sodium ions cannot enter. So cannot enter. They are blocked from entering. However, it has now become permeable to potassium. So now potassium can actually go through the membrane, and what they do is potassium leaves. Potassium diffuses out of the neuron, and this sets the membrane's charges back to normal. It repolarizes or restores the inside of the membrane to be less positive than the outside. So here is my repolarization. Notice that I get my positive back on the outside, my negative back on the inside because my potassium rushes out. Now, one thing you're going to notice is that the sodium and potassium are now on opposite sides of the membrane of where they need to be. So these initial conditions of sodium potassiums have to be restored back to their original positions. And we do this through something called a sodium potassium pump. And this pump uses ATP to restore the original configuration. And when I say original configuration, I mean sodium on the outside and K plus on the inside. During the sodium potassium pump, 3 sodium are going to be ejected to the outside of the cell and 2 potassium are going to be brought inside the cell. And until repolarization actually is complete, the neuron cannot conduct another nerve impulse. So here's an example of the sodium potassium pump restoring everything back to their normal conditions. We have potassium coming in and sodium going back out to their original spots that they need to be. Note that this pump right here uses ATP. And that is the end of today's lesson. Please let me know if you have any questions and I'll be more than happy to help. Otherwise, I hope you have a great day.